Hi, I'm Miss Hearn. Let's get started. In this video, we're going to solve an equation which contains a radical in two different ways. The equation is b plus 4 times the square root of b equals 21. It's the square root that makes this a radical equation. When solving a radical equation with a square root in it, one method is to isolate the radical term, square both sides to get rid of the radical, and then solve the resulting equation. To isolate the radical term, I'm going to subtract b over to the right-hand side of the equation, leaving me with 4 times the square root of b equals 21 minus b. Now I'm going to square both sides. On the left, the 4 is being multiplied times the square root of b. When factors are being multiplied and then we square them, all we have to do is square each part. 4 squared is 16, and the square root of b squared is just b. That's the reason we decided to square both sides of the equation. However, on the right, we don't have multiplication between 21 and b. We have subtraction. And when we have subtraction or addition, you can think of it as foiling 21 minus b times itself. First times first would be 441. Last times last is going to be a positive b squared. And in between, we'll have double the product of 21 and negative b. Negative 21b doubled is negative 42b. The equation that we have now is a quadratic, and you can tell this because the b is being squared. So this is an improvement because we got rid of that radical, and now we know that we can solve a quadratic equation using one of our quadratic methods. Let's get it in standard form to get an idea of which method we might use. Standard form means 0 on one side and descending order on the other. So I'm going to subtract 16b from both sides. I'm going to write b squared first. Then negative 42 minus 16 would be negative 58b. Plus, we have a positive 441. It's possible this quadratic equation could factor easily. And if it does, that would be the best option. We could quickly check factors of 441 that might add up to a negative 58. 441 is not even, so 2 won't go into 441. It ends in a 1, which means that 3 and 7 are likely candidates. If we multiplied a negative 3 times a negative 147, we would get a positive 441, but they wouldn't add up to negative 58. 4, 5, and 6 definitely won't divide into 441. Let's try negative 7. Negative 7 goes into 441 negative 63 times. Unfortunately, those would add up to negative 70, so that's not going to help us. 8 definitely won't go into 441. Let's check 9. It looks like negative 9 will go in negative 49 times. And that's great because negative 9 and negative 49 add up to negative 58. So this trinomial does factor into b minus 9 times b minus 49. Now, if you didn't notice that, you could use the quadratic formula and solve. But since we did, we can see quickly that 9 and 49 satisfy this equation. But do they satisfy the original equation? Anytime you square both sides of an equation, you create the possibility of extraneous solutions. The reason for that is that, for example, while it might not be true that negative 3 is equal to 3, that would be a false statement. If I were to square both sides, it would be true that 9 is equal to 9. So you can turn a false equation into a true one by squaring both sides. So to make sure that these values actually make this equation true, and not the squared version, we have to plug in and check. Checking in the original equation, plugging in 9, we would have 9 plus 4 square roots of 9, and we want to know, is that equal to 21? Well, the square root of 9 is 3. This term is actually 12, and yes, 9 and 12 would be 21. Let's check if we used 49. 49 plus 4 times the square root of 49 is definitely not going to equal 21, because if you add anything to 49, it's only going to get larger. So the final solution set will only include the number 9. I hope you found this video useful. If you did, please remember to like it. Method number 2, using u-substitution to solve the same equation, is featured in my next video. Follow the link.